Welcome everybody to another virtual session of seminary analysis of the Departamento de Matemáticas, Universidad Autónoma Metropolitana Iztapalapa campus. Today, it is a pleasure to introduce Professor Jasang Yoon from the School of Mathematical and Statistical Science of the University of Texas. Professor Yoon got his Bachelor of Science in Mathematics in 1991, the Master of Science in Mathematics in 1993 in Seungju Kim Hwan University, Seoul, Korea, and his PhD of Mathematics in the University of Iowa. I can say that the Professor Yoon has a lot of contribution of research papers of high impact, and in his research line, we can find matrix computation and theory, multivariable operator theory, C-star algebras, several complex variables, classical theory of moments, and mathematics education. Today, Professor Yoon is going to talk about norm and numerical radius of bounded linear operator. So, Professor Yoon, please, you have the space.
Okay, yeah, thank you very much to your invitation in your seminar. Okay, so I'm gonna using the pen table, and then when I speak, I'm gonna writing. This is actually my talk, norm and numerical radius of bounded linear operator. And here is over, everybody can see, over the last several decades, many peoples actually from here, the Batias and Davis and the Foyas and Ko and Kitani and etc. Many people have studied operator norm inequality for n by n complex matrix and operators defined on B of H, and where H is complex Hilbert space and B of H is algebra of bounded operator. This is the algebra of bounded operator. Actually defined on H.
The Hilbert space is not necessarily separable, right?
What's it again?
It's not separable, not necessarily separable. The Hilbert
No,
space.
not actually is not separable. Yeah, just is a complex Hilbert space. But
It's
usually
complex.
usually I'm gonna study the separable Hilbert space. Yeah.
Okay.
And actually they have studied the following highness type inequality. Actually, the first one is the for A, B, X belongs to B of H. B of H. Oh no, it's not B of H, I'm sorry. This is the complex matrix. We say Mn complex numbers. And then it's the 2 times A star XB. This is the matrix norm less than A star AX plus X BB star. I want to say this is the one, okay? Where this is the norm, but the specific this norm is the means unitary invariant norm. Here, actually that is norm is a UXB. What is the meaning of the unitary invariant norm? This is the exactly X for all unitary UMB belongs to M and C. And from here, A star denotes the adjoint of A. And then also they studied for A, B, X. This is belongs to Mn. This is a complex number. This is the M by N complex matrix with A and B both are positive, semi-definite, and for R belongs to N0 and 1. Okay. So that case is okay. Everybody can see. And actually, so they studied. Okay, sometimes I cannot find out the course over here. Okay. They studied 2 times A 1/2 XB 1/2. This is the norm. This is a unitary invariant norm. From here, AR XB 1 minus R plus A 1 minus R XB R, which is the less than or equal AX plus XB. So I want to say this is the 2. Okay, and actually but the Davis proved this is the inequality 2 actually in the data paper. This is the SIAM journals. Metrics. This is the analysis and applications.
Is he the Bhatia that wrote the book on matrix analysis?
Yes.
The same Bhatia?
Yeah. Actually, yeah. I think it's the Bhatia. Yeah.
Okay.
And using the convex function, the convex functions on 0 and 1. So that convex function is the FR. This is the norm. AR XB 1 minus R plus A 1 minus R X B to the R. This is a norm. Actually, this is a convex function obtained is maximum at R is 0 and 1, and minimum value, minimum at R is 1/2. Here, the first I'm gonna just give it to the, this is the question one. Question one. Here is a, can we prove? Actually, this is the inequality tool for any real numbers R with invertible positive semi-definite operator A and B, which is belongs to B over H. And X is arbitrary. X is arbitrary in B over H. This is actually, we can ask ourselves, because it's the Bhatia Davis, only they prove that R is the between 0 and 1. And then also in the, this is only work for the metric space. This is n by n complex metric. This is actually the finite. And then it's, we can ask, can you prove this is the dead inequality for arbitrary in real numbers R? And then is, can you extend the dead one is the operator is A and B. This is the first our questions. And the later around the 2014, from here, actually the Conde and Core and Singh improve. This is the inequality tool using the shoe product. Sometimes we call Hadamard product. They're gonna prove in the LAA, linear algebra in each application 2014. As follow, actually, this is the 2 times unitary invariant norm. A is alpha plus beta over 2 x b times 1 minus alpha plus beta over 2 plus a 1 minus alpha plus beta over 2 x b alpha plus beta over 2. This is the unitary invariant norm. This is less than or equal. Here they split the a alpha x b 1 minus alpha plus a 1 minus alpha x b alpha plus a beta x b 1 minus beta plus a 1 minus beta x b beta. I want to say this is the number 3. So question 2 is, can we prove actually that inequality 3 on B of H with A, B, X from here, AB is a invertible operator. Invertible operator. Invertible, and actually I want to say is a positive semi-definite. In here is this is a Kondeco and Singh. They didn't prove yet for the last inequality. Actually, I want to say including. This is the last inequality here. 2 times ax plus xb. This is actually our question. So in our papers, we completely proved the question 1 and the question 2. So from here,
Professor Yoon, the improved inequality alpha and beta runs over of the unitary interval.
Oh, I'm sorry. Here is the alpha and beta is the old alpha and beta is the old alpha and beta is the real numbers.
Okay.
Yeah. So actually, they improved the from the unit interval to arbitrarily in the real numbers alpha and beta. Okay. But they only proved that only the finite dimensions. So from here, for the answer of question 1 and 2, actually we recall the definition of the elementary operator. We call this LA, RB, LA, and RB acting on B of H. Okay, for A and B, this is the bounded linear operator, B of H. And then we say let, what is LA? This is what we call left multiplication, called left multiplications. And RB, this is a called right multiplication. Right multiplication on B of H, such that actually this is operator X, and then we just acting at A. What is the meaning of this one? Actually, just multiply A and then X. And from here, this is RB, this is the X, and then we just multiply B. From here, this X is B of H. And this is actually our theorem, theorem 1. Let A and B belongs to B of H. This is invertible, and self-adjoint operator, and let just a little cursor down. I'm going to define for the tau. This is a tau acting B of H, B of H to B of H, B of H. So from here, X just go to AX, B inverse plus A inverse XB. We just acting. And then actually, then we have 2 times norm over X. This is a less than or equal. This is the tau X. This is the operator norm. Okay, so I want to sketch. This is the sketch of the proof. So first we prove that 2 times X. This is the Hilbert-Smith norm. This is the Hilbert-Smith norm. This is this is the norm tau X. This is the Hilbert-Smith norm. Okay, where what is the meaning of the HX? This is the Hilbert. Schmidt norm. Actually, that is so actually the norm of the square and then Hilbert-Schmidt norm. This is inner product. I want to say the Hilbert-Schmidt. What is the definition of this one? This is the trace X star X. What is the meaning of this one? Actually, this is the I from 1 to n Si square X. And what is the meaning of this one? Si X. This is the means the singular value of X. This is the n by n complex matrix. So what is the meaning of the singular value? This is the square root of the eigenvalues of X star X. Okay. So why is do that? First, I'm gonna prove the. Actually, I'm gonna sketch for the first step here. Why is do that? Actually, we're gonna consider the commuting pair. Commuting pairs. Here A and A inverse. This is to automatically commute each other, and B and B inverse. And I'm gonna I'm gonna consider the 4 tuples. That 4 tuple is the LA inverse, RB inverse, and RB. Okay, and then also recall the Taylor spectrum. I'm going to explain what is the roughly what is the meaning of the Taylor spectrum. LA inverse, RB inverse, and RB. This one is Taylor spectrum of the A and A inverse. Cross product, Taylor spectrum, B inverse, and B. This one is actually and Coulter and Fialkov. They proved 1987 general function analysis. They proved it over this one. And then this is we just to recognize this is exactly alpha and alpha inverse. This is a pair. And where is alpha? Alpha is a spectrum of the A. And this is exactly cross product. And then this is we say beta and beta inverse over here. And beta, this is the beta is belongs to spectrum of the B. Okay. And actually, what is Taylor spectrum over here? This is the for a. I'm only considering the commuting pair. Commuting pair. I want to say this is the T1 and T2. We consider a short causal complex. Causal complex. I want to say K and then T, we just acting Hilbert space such that here this is the 0 and then go to the 1 Hilbert space. This is a 1 Hilbert space and direct sum and the other Hilbert space. And then go to the 1 Hilbert space and then this is the go to the 0. For here, I want to say this is a K -1. This is the 0 operator. And then is the K0, I'm gonna here is this is a column operator T1, T2, and here is a K1. I want to say this is the negative T2, this is a pair, and then here is a K2, this is the zero operator. So we want to say if the range of the Ki exactly same to the corner, this is a Ki plus 1, where is I belongs to -1 and 0 and 1, and then this is a causal complex acting Hilbert space is said to be exact. Okay, so what is the Taylor spectrum over here? So Taylor spectrum of that commuting pair. This one is all the collection of the lambda 1 and lambda 2 belongs to two-dimensional complex number is pair. So here is we're gonna consider causal complex is a T1 minus lambda 1. Actually T2 minus lambda 2 acting Hilbert space is not exact. Is not exact. So this is the definition of the Taylor spectrum. And then based on that acting, and then we're gonna consider a map. Consider a map. This is the polynomial from complex the 4-dimension to complex number. So given by this is the map P Z1 and Z2 and W1 and W2. This is the acting Z1 W1 plus and Z2 and W2. Okay, and then this is the this is a spectrum of the tau. This is a spectrum. This one is a spectrum of a single operator. Okay. This is a spectrum. What is a tau? Tau is the LA RB inverse plus LA inverse RB. Actually, why is do that? The tau x acting AXB inverse plus A inverse XB. So this one is exactly, this is a polynomial LA inverse. This is the RB inverse. This is RB. So this is by definition of that map. From here. And then this one, I'm gonna just take out the P. This is the spectrum, but this is the single operator spectrum, but this is become pair, this is a 4-tuple and then becomes a Taylor spectrum, LA inverse, RB inverse, and then this is RB. So this is what we call spectral mapping theorem. This is a spectral mapping theorem. Okay. And from here, what is this one? This one is actually Taylor spectrum. This is the A and A inverse, cross product, and Taylor spectrum, B inverse, and then B. This is a Coulter and Fialkov and general function analysis. This is the result. So if you just look at carefully, and then this one is exactly pair is alpha and alpha inverse. This is alpha is belongs to spectrum of the A, and this one is a beta inverse, and then beta. This is the beta is belongs to spectrum of the B. Okay, so this one is by definition again, over the here. Acting over here. So on this one, we say this one is alpha beta inverse plus alpha inverse and beta. From here is alpha is belongs to the spectrum of the A, and beta is belongs to the spectrum of the B. Okay, so this one is exactly alpha square plus beta square over alpha and beta. Exactly the same situations. So this one is less than 2. Okay, because it's why is do that? Because it's A and B both are self-adjoint. And invertibles. So this is a self-adjoint. A and B is a self-adjoint. So that case, the spectrum of this one is a real numbers. Actually, alpha and beta is a real numbers. And also, if lambda belongs to spectrum of the tau, and then actually absolute value lambda is bigger than 2. So based on this one, so actually this is the first step. Actually, we prove. Do you have any questions so far? So currently, this is the first step is a let. This is the let. This is the m small number tau we call infimum numbers. Over the lambda is belongs to spectrum of the tau. Actually, we know this is a less than, this is the bigger than 2. And then we already, this is the first step. This is the tau x and the Hilbert-Schmidt norm. This is the bigger than m tau. From here is the norm of the x Hilbert-Schmidt norm. And that case 2 times and then Hilbert-Schmidt norm. So here actually to prove of this one, we need to make the theorem. This is another theorem. So let A is A1 and A2 are A2. and B, this is the B1 and B2. This is the commuting pair, actually pairs or operator acting on B of H. So here is the lead. This is the F is, this is the continuous function acting on the Taylor spectrum and then also Taylor spectrum of the B. And X is belongs to C2. This is we call Hilbert Smith class. Hilbert Smith class. And then we can prove that LA RB, this is the acting X, this is the Hilbert Smith norm. This is the bigger than or equal infimum of the fxy. This is absolute value times norm of the X, Hilbert Smith norm. I'm just let me make the bigger. Okay. This is Hilbert Smith norm. From here is the X and Y belongs to Taylor spectrum of the A, cosine Taylor spectrum of the B. Actually, after we proved this theorem, so this one is exactly this one, exactly this meanings. So therefore, we prove that this is the 2 times X and Hilbert Smith norm less than or equal. This is the tau X. Hilbert Smith norm. Okay, and then how can we improve from here 2 times X, and then this is the unitary invariant norm, and from here is the tau X. This one is unitary here. Unitary invariant norm. So from here, we using the Keyfan's dominance. Keyfan dominance theorems. Any other, but still, this is the unitary invariant norm on m by n complex matrix on Mn and C. So what is the Keyfan dominant theorems? Actually, I'm gonna just simply here Keyfan I want to say Keyfan theorems. Here let X is X1. Here is Xn. This is the real numbers, Rn. And also Y. And this is Y1 and Yn. Real numbers. but still with some relation x1 bigger than equal x2 xn, also y1 bigger than y2 yn, and then here is a summation I from 1 to k xi bigger than or equal summation from I from 1 to k yi for all k from 1 to n. Okay, and that relation if and only if this is the x norm bigger than or equal y norm for all unitary invariant norms. So from here, using the keep-on dominant theorems, we can extend that is a Hilbert-Sumin norm to unitary invariant norm. Okay, and then after that, this is only acting on finite dimension. How can extend this is infinite dimension? This is the B of H. Okay, so that one actually we prove that this is the another theorem over here. This is the another theorem. This is for a net of operator, actually a alpha. So a alpha converted to strong operator topology, and then this is the norm a alpha. Actually, this is a converted to the norm topology. Here is norm. Okay. So based on that fact, we can extend to from the finite dimension to infinite dimensions. I'm a little bit explain over here. This is actually we can find out the PF. This one is F belongs to some here. This is actually the finite dimensional this is the orthogonal projections. Orthogonal projection converted to the identity operator I in strong operator topology. Okay, so we just using that idea, we extend to finite dimension to infinite dimensions. Any other questions so far? So this one is actually using a similar proof used in theorem 1. We also have this is a theorem 2. We extend this one to the answer of the question 1 last time I explained. So from here is a 2 times a 1/2 xb 1/2. This is we extend AR xb 1 minus r plus is a 1 minus r xbr. This is the norm is less than ax plus xb. Okay. And also theorem 3, we also extend this one. This is a alpha plus beta over 2. Here is the every r in real numbers. And here is the a and b is a self-joint. Here is the a and b positive. Actually, the invertible, positive, semi-definite. Okay, and then from here, x b 1 minus alpha plus beta over 2 plus a. Here is a 1 minus alpha plus beta over 2 xb alpha plus beta over 2. This is a norm less than here a alpha xb 1 minus alpha plus a is a 1 minus alpha xb alpha plus a beta xb 1 minus beta plus a 1 minus beta xb and beta, and still using these 2 times ax plus xb. So using the similar proof, we extend the number 2 and number 3. This is actually answer for the question 1 and question 2. And we also in the theorem 4, we extend this is the norm to w. This is the numerical radius. So now I give to the open question here, and this is actually the open problem. Many years, they only consider the even the Fouriers and everybody. Could you check here is a theorem 2 and theorem 3, and what is the order of this one? Here is the a xb, and then this is also a and b, right? Could you extend this one? Maybe could you change this one to this is I'm concerned here. The between is AR XB 1 minus R plus A 1 minus R XB R. Could you change this one to the A R XB 1 minus R plus B over here? This is a 1 minus R A. So could you change this order from the A to B? Could you change to the B to A? And they still work in the all the inequality or not? This is my concern. But I look at the many paper, and then it's nobody work over this one. So this is actually my questions. Any other? This is everything. I'm sorry because I want to explain more detail, but this is almost 6 o'clock. So I just look at the time and then I introduce the open question. Yeah, that is everything is my talk.
Thank you so much, Professor Yoon. With thanks to the professor. I think we have as a couple minutes to ask some questions. So does anybody has a question?
May I ask?
Yes, please, Professor.
Very interesting, your inequalities. But do you have in mind some other applications apart from the application to numerical radius?
You mean the several application for numerical value? What?
No, another different applications apart, different from the numerical radius. Do you know another application of your inequality?
Oh, I don't know about that one. The very interesting is this is all the inequality of the norm. Still, we prove the numerical radius, radius, and then because it's sometimes the norm inequality doesn't work for the numerical radius, but we have another idea. Maybe it's hopefully I'm going to present is the next time. Using the new idea, we exactly prove that norm inequality to numerical radius. Yeah, but application, I don't know. Yeah. Because it's the, this one is the almost is a 20, 30 years, and the many mathematicians improve the small thing, and then it's two inequality they got it, but we just prove only for the finite dimensions, but we success to improve the infinite dimensions in the Hilbert space, and then now is the suddenly I concern why is the order is AXB and AXB. Is there any possible AXB and then BXA? Because it's A and B is a change. But I checked the many paper, but nobody work that one, because it's the one reason is this is the kind of the relation to the arithmetic and geometric mean of the operators, but maybe change it to the order, and then is there is no, I don't know. Yeah. And even though that proof is based on the convex functions. Convex function is they checked the convex function AXB and AXB. This is that order. They checked the convex functions. Actually, that convex functions come from the 1 minus p. This is the 1970 or 80 is some person developed that convex theory. That actually come from there, and some kind of change of variable, and then is p is from the -1 and 1, but the new change of variable and then 0 to 1. So using the convex function, actually that is that convex function has a maximum, and r is 0 and 1, and minimum in the 1/2. So they can prove that inequality. But if I change the order, this is a convexity doesn't work anymore, and then I try to develop the theory, but it's almost in 3 and 4 months is nothing. So I have no reference.
Okay, thank you.
Yeah.
The conditional commuting pairs of the theorem above is important of the proof of this theorem,
because it's actually it's a Lubin-Hart, because it's why we study for the commuting pairs, because if it's a commuting, we're going to consider Taylor spectrums. But if it's not commuting, and then it's other people still work in the non-commutative algebra, but there is no, we do not mention any the Taylor spectrum. But this is actually idea is come from the Taylor spectrum and the open mapping theorem for the Dale result. But there is no commuting condition, and we cannot using the open mapping theorem for the, no, not open mapping. I'm sorry. spectral mapping theorem. We cannot using anymore.
Yeah.
So that's the reason we only focus on the commuting pairs, because it's we consider Taylor spectrum, and then it's the Taylor spectrum from the causal complex over there. So using the causal complex, and then is we using the spectral mapping theorem. So that's the reason we're concerned about the only commuting pairs. If it's not, and we have no tools. So that's the reason is Rubin Hart mentioned that we need any condition of the commuting. So one is the maybe doubly commuting, this is too strong, or maybe commuting, or maybe other commuting condition. Yeah.
It is my first time that I see the Taylor spectrum. So do you have a reference that I can find this definition, a formal definition of the Taylor?
Oh yeah, it's actually Taylor is a 1980. 1980 is he developed the Taylor spectrum, but after that, Raoul Coulter, because it's a Taylor using some strange symbols, and then it's very difficult to understand. After that is Raoul Coulter. Raoul Coulter kind of organize all the Taylor spectrum, and then is a spectral mapping theorem, and then also left spectrum and right spectrum, and then is all the spectral condition Raoul Coulter developed. After that, my thesis, I also developed my thesis after that, and then maybe you just go to my paper, and then it's sometime is the long time symbol is a kind of complicated, and so maybe best reference is Raoul Coulter papers, and also is my papers.
Okay, thanks.
Yeah.
Thanks, Lourdes, for the information.
Yeah.
So does anybody has another question for the professor? If done, we thanks again to the professor. Thanks, professor.
Okay, thank you. Yeah, thank you everybody, and then is see you in the September, hopefully, in the Edinburgh. Okay.
Hopefully.
Okay. Bye bye.
Bye. Thanks.
Bye, Jasang.
Bye.
Thank you.
Bye.
Bye, Sasha.
Bye.